Okay, so we have taken a look at probability basics in Module 3A. Next, we need to look at what's called conditional probability and the idea of independence. Before we dive into Module 3B, which is going to be fairly brief, I'd like to do a quick summary of the important ideas and formulas that we reviewed in Part 3A. Okay, so first of all, we have this idea of an outcome. An outcome is a specific observation or a specific possibility when you run a trial, draw a card, flip a coin, roll a die, pick a sample from some population. Okay, so it is some single possible observation. For example, we might flip a coin and get a head. That's one outcome. We might roll a die and get a 3. That's one possible outcome. We might draw a card from a deck of cards and get the king of spades. So that's a possible outcome. We might have a bag of marbles of different colors and, that we can't see inside of, and we might reach in and draw out a red marble. So that's one possible outcome. We might randomly select a person and check their eye color and discover that this person has brown eyes. Or we might select a person randomly and ask them about their diet and learn that this person is a fruitarian, so only consumes fruit. Now, an event, which is usually what we talk about when we're actually stating probabilities, is some set of these possible outcomes, depending on the trial or experiment that we're performing. Now, flipping a head is one possible outcome when you flip a coin. We can have a set of just this one possible outcome, and we can talk about, okay, what is the probability of flipping a head? If we're rolling a die, we can ask, what is the probability of rolling a -4? Well, this is fine. It is not possible to roll a -4, so this event is the empty set, and the probability of the empty set occurring, the probability of getting a -4 is 0. If we draw a card from a deck of cards, what is the probability that we're going to draw a heart? Okay, well, there's 52 cards in the deck, assuming we don't have any jokers. And so 1 out of 4 of these cards is going to be a heart. Our probability of drawing a heart is therefore going to be 1 out of 4. What is the probability when we reach in our bag of marbles that we draw out a marble and discover that that marble has some color? Well, here, the event is the set of all possible outcomes. Every marble has a color, and so if we talk about the probability of drawing a marble that has some color, that's going to be, the probability is going to be 1, or 100%, that if we draw a marble at random, we get a marble that has a color. Rather than selecting a person that has brown eyes, we could talk about selecting a person that has blue or gray or green eyes. We could talk about selecting a person at random and discovering that that person only eats rocks. Well, that's, the probability of that is 0, I certainly hope. All right? So, outcomes are individual observations, and events are sets of outcomes that we are trying to predict probabilities of. The probability of some event A is guaranteed to be some number between 0 and 1 inclusive. The complement of A is any outcome that occurs, or any set of outcomes that occurs that is not in event A. We denote that complement of A by tilde A, and it's guaranteed that the probability of the not A event is 1 minus the probability of the A event. We use the set intersection symbol with events. Here we're designating or describing the probability that both event A and event B occur. And with the union symbol, we're specifying here the probability that the event A or the event B occurs. Now, if we know the probability of A occurring and the probability of B occurring, and we can figure out the probability of both A and B occurring by examining possible outcomes or sets of outcomes, or by knowing proportions of the population of people with brown eyes, people with blue eyes, people with green eyes, we can compute the probability of A occurring or B occurring as the sum of the probability of A plus the probability of B minus the probability of both occurring, because we will have double counted that by adding together the probability of A plus the probability of B. Sometimes two events are mutually exclusive, in which case, the mathematical specification of that is the probability that both A and B occur is 0. And in this case, if the probability of A and B occurring is 0, then we can compute the probability of A occurring or B occurring as simply the sum of the probabilities of A and B. All right, so that's a hasty summary. Onward to conditional probability and independence. Okay, so the notation that we use for conditional probability looks like this. P of, and then in parentheses, A vertical bar B. And we pronounce the vertical bar as given or given that. So P of A vertical bar B is read as, tell me the probability of A occurring given that B has occurred. In effect, what we're doing is, instead of considering the entire universe of all possible outcomes here, we are narrowing our universe to the sub-universe in which B has occurred, and then we're asking, within that sub-universe, what is the probability that A occurs? We can actually compute that by, if we know the probability that both A and B will occur, and we divide that by just the probability that B has occurred, the result that we get is has to be the probability of A occurring given that B has occurred. All right, so let's do a real example of this. Let's suppose that we are rolling 2 dice, and the dice are labeled. That is, we have dice number 1 and dice number 2. A is the event that we get 7 as the sum of the pips on the 2 dice. B is the event that the first die is a 4. Okay? Well, we computed A previously. We know that if you have 2 dice and you roll them, the probability of getting a sum of 7 on the 2 dice is 1 out of 6. That is, there are 36 possible outcomes, and 6 of those outcomes, namely 1 plus 6, 2 plus 5, 3 plus 4, and so on, 6 of those outcomes result in a sum of 7. So the probability of A, just considered all by itself, is 1 out of 36. 1 out of 6. Pardon me. The event B, that the first die is a 4, is 1 out of 6. All right, there are 6 possible outcomes for die number 1, and the probability that is a 4 is 1 out of 6. So we ask ourselves, all right, what is the probability of A given B? That is, what is the probability that the sum of two dice is going to be 7, given that the first of the two dice has a value of 4? Alrighty? Well, that probability, the probability of the sum being 7, given that the first die is a 4, is only 1 out of 6, because when we look at the second die, there are 6 possible outcomes from the second die, but if the first die is known to be 4, only one of those 6 possible outcomes, namely the 3, will get us a sum of 7, given that the first die is a 4. All right, so let me write that down. So the probability of A given B is 1 out of 6. That is the probability that the second die is 3, because the first die is 4, all right? All right. Well, so we know now the probability of A given B is 1 over 6. And we're asking, what is the probability of A and B? Okay, given that we know the probability of A given B, well, we can compute the probability of A and B, that is, the probability that we roll a 7 and that the first die is a 4. From our definition, we just move the probability of B to the other side. It's going to be the case that this is going to be the probability of B times the probability of A, given that B is true. Actually, that's usually written the other way around. It's usually written as probability of A given B times the probability of B. Okay, this is just an alternate way of writing our definition of conditional probability. Okay, well, we have the probability of A given B. We just figured out that that was 1 over 6. And we also know the probability of the first die being 4. That value is also 1 over 6. So the probability of the sum being 7 and the first die being 4 is 1 out of 36. Okay, we just multiply the probability of A given B times the probability of B, and that will give us the probability of A and B. Now, does that actually make sense if we think about this in terms of possible outcomes? Okay, well, the possible outcomes for A, that the sum is 7, are the sums 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1, right? So those are the possibilities for A. I should write this down. So we've got 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. So there are 6 possible outcomes of 36 total outcomes in which event A is true. Now, from these outcomes, the only one of these where B is true, that is, that the first die is 4, is the one where the second die is 3. And so we can deduce by just looking at the set of available outcomes that there's only one outcome out of 36 outcomes in which both A and B are true. So the computation 1/6 times 1/6 does give us the correct result that we can just compute directly, which is 1 out of 36. Okay, so that's conceptually what conditional probability is. Now, so from this formula or equation, probability of A given B is defined to be the probability that both A and B occur divided by the probability of B occurring. We rewrite that to say that the probability of A given B is equal, just multiply both sides times the probability of B, probability of A given B times the probability of B. And it shouldn't take you more than a moment to realize that also means that the probability of A and B, well, the probability of A and B is the same as the probability of B and A, and so that's the same as the probability of B given A times the probability of A. Okay, this is the basis for what's going to be described in the next module as the law of total probability. Okay, now what if two events, are independent? That is, the occurrence of one event has nothing whatever to do with the occurrence of some other event. For example, instead of rolling 2 dice and computing the sum, we might roll 1 die and select one person and ask, okay, what is the probability that our person has brown eyes given that we rolled an odd number? Well, clearly, in that case, the probability of our randomly selected person having brown eyes is completely independent of what we rolled on our die. We say, mathematically, that 2 events are independent if the probability of one event given the other event is simply the probability of that. Okay, so the probability of event A given event B is simply the probability of A without considering B at all. And in fact, in this case, the probability of A given B is also going to be the same as the probability of A given not B. To consider my silly example again, the probability that our randomly selected person has brown eyes, given that the die we rolled was odd, is going to be the same as the probability that the person has brown eyes, given that the die we rolled was not odd, that is, was even. And in turn, that's just the probability that the person has brown eyes, period, not considering the roll of the die. Okay, let's take a look at some specific examples to identify which of these are independent and which are dependent. So our event A is going to be that we get heads on the first toss of a fair coin. And our event B is going to be that we get tails on the second toss of that coin. Now, if this is a fair coin, and we're not doing any kind of strange magic trick or fraud, does the second coin toss have any dependency on the first coin toss? No, not at all. It doesn't really matter what the first coin toss is. Okay, the probability of B, the probability of getting tails on the second toss, is 0.5. The probability of B given that we got a head on the first toss is still 0.5. And consequently, because the probability of B given A is equal to the probability of B, we are justified in saying that A and B are independent. Okay, now next, the event A is that a MISM student is 200 centimeters tall, and the event B is that that individual is a woman. Probably not a woman, just one. All right, so let's consider that, just made up number, that if we pick a MISM student at random, the probability of that person being a woman is 0.33. I think it's actually higher than that nowadays. And we ask, what is the probability of the student being a woman given that this person is 2 meters tall or taller? Well, that's probably going to be less than 0.33. Someone being 2 meters tall reduces the probability that that person is a woman, at least in the in the population of students that we see. And so in this case, because the probability that the person is a woman, given that they are more than 2 meters tall, is going to be less than 0.33, and therefore these are not independent traits. Okay, another example. Here, the first event is that we get heads on the first toss. B is that we get tails on the first toss. These, keep in mind, are mutually exclusive events. We're comparing the event that we get a head on the first toss with the event that we get a tail on the first toss. Now, the probability that we get a tail on the first toss is 0.5. The probability that we get a tail on the first toss, given that we got a head on the first toss, that probability is 0. If we got a head on the first toss, we cannot have gotten a tail on the first toss. And again, since these probabilities are not equal, these are not independent events. Okay, so to summarize and generalize a bit, because of the way we have defined the probability of some event given some other event as the probability of both events divided by the probability of the second one, just by algebra, you can conclude that the probability of both A and B occurring is equal to the conditional probability of A occurring given that B has occurred times the probability that B has occurred. All right? Now, if A and B are independent, then the probability of A given B is simply the probability of A. And consequently, in that case, the probability of A and B occurring, if A and B are independent, is simply the probability of A times the probability of B. And we can generalize that to some arbitrary number of independent events. We select a person and look at their eye color. We select a person and ask them about their dietary habits. We roll a die and see what we get. We flip a coin and see what we get. We select a ball out of a bag and test whether it's red or not. These are all completely independent of each other. So the probability that we have a brown-eyed vegetarian and we flipped a head and we rolled a 4 and we selected a blue ball, well, the probability of all of those events occurring is simply the probability of each one of them all by themselves. So the probability of someone having brown eyes, period, times the probability of someone having someone being a vegetarian, times the probability of now I've forgotten what values, selecting a blue marble, etc. Okay. Bear in mind that mutually exclusive events are not independent, because the probability of one event occurring, given that the other event has occurred, is always 0 if the two events are mutually exclusive of each other. Okay, that's all we're going to do for the moment. I will describe. Well, let me skip over the Challenger disaster here. Let's take a look at one of these tests of understanding here. I'll come back and do the Challenger disaster in my next live lecture. All right, so we're going to roll a 6-sided die 3 times. We want to calculate the probability of getting a 2-2-2 when we do that. Well, each time we roll a die, that probability is independent. So we can simply multiply together the probability that we get a 2 on the first roll times the probability we get a 2 on the second roll times the probability we get a 2 on the third roll. And that's going to be 1 over 6 cubed. I can't compute 6 cubed in my head. So the probability of these 3 rolls occurring, 2, 2, 2, are 1/6 times on 6 times on 6. And in fact, that's exactly the same as the probability of rolling a 1 followed by a 3 followed by a 4. 1/6 times 1/6 times 1/6. Notice in this case that the order of the rolls does actually matter. So the probability of rolling a 1 followed by a 3 followed by a 4 is the same as the probability of rolling a 3 followed by a 4 followed by a 1. Okay, because in this case, the order of these rolls does matter. Okay, now we're going to roll a 6-sided die and flip a coin. What is the probability that we roll a 1 or a 2 and get heads? Well, again, the die roll and the coin flip are completely independent of each other. The probability of rolling a 1 or a 2 is 2 out of 6, so that's 1/3. And the probability of getting heads, we'll assume that this is a fair coin, is 0.5. So 1/3 times 0.5 is 1/6. This last one here, we roll a 6-sided die and flip a coin. And what is the probability that we roll a 1 or a 2 or get heads? Well, again, these things are independent of each other. So the probability of rolling a 1 or a 2 is 1 out of 3. The probability of getting heads is 0.5. Let's write this stuff down so that we don't make a silly mistake. So the probability of 1 or 2 is 1/3. The probability of heads is 0.5. Now, we know from our formula that the probability of 1 or 2 or heads is equal to the probability of 1 or 2 plus the probability of head minus the probability of both of those occurring because we need to eliminate the double counting. So that's the probability of 1 or 2 and heads. Well, here, independence helps us in this third term here. The probability of getting a 1 or a 2 for our die and getting a head for our coin, those are independent events. So this term just becomes the probability of 1 or 2 times the probability of getting a head. And now we can just throw in the numbers and figure this out. So we've got the probability of getting a 1 or a 2, which is 1/3. We've got the probability of getting a head, which is 1/2. And we've got the probability, this is going to be subtracted, the probability of getting a 1 or a 2 times the probability of getting a head. All right, so 1/3 plus 1/2 minus 1/6. That's going to give us 1/6 plus 1/2. 1/6 plus 1/2. Now I can't do I can't do simple arithmetic in my head. Okay, so this is going to be 2/3, right? Yeah, 2/3. So it's going to be 3/6. I'm sorry, 4/6. 1/6 plus 3/6 is 4/6 is 2/3. All right, so we've got a 2/3 probability of either rolling 1 or a 2 or getting heads when we flip our coin. Okay, there we go.